my viewers across the globe, the professor, Ajasin Prof, Ajasin Prof, ladies and gentlemen. I am Adedowole Alimi from Nigeria. I'm presenting a paper titled Vibration Analysis of Prismatic Rayleigh Beam on Vlasov Flexible Foundation subjected to fast-moving several load. The study of vibration analysis of load on structural elements has a wide application on our day-to-day activity of human endeavors. Some of practical applications include the response of railroads to traveling trains, the response of bridges and elevated roads to mobile vehicles, to mention but few. Currently, the rate at which vehicles are moving have been increased considerably, and the weight of such vehicles has been on increase. On the other hand, due to economical requirements, the bridge structures carrying these moving loads are made up of lighter structure. Due to lighter nature of the structure under heavy moving load, severe vibration and dynamic stresses are experienced. In order to safeguard life and property, this has necessitated the pursuit for accurate appraisal of vehicles track interface during the course of heavy subsystem. Some of the notable researchers are Oni, Sadiq, Private, to mention but few. Problem statements. The Rayleigh beam resting on Vlasov flexible foundation is subjected to the following conditions. 1. The beam is prismatic. 2. The beam material properties such as moment of inertia of the beam and modulus of elasticity are constant. 3. The shear force and stiffness of the foundation are constant. 4. The beam is thick because statutory inertia is considered. 5. The beam is simply supported, that is pin end. 6. The loads applied are acting as a point on the. We have two cases. Case 1 for regular load. The governing equation is given by equation 1. Then the right hand side represents the load, which takes the form of equation 2. Here we are considering only the gravitational force effect. We neglected the moving mass effect. Thereby we have equation 3. And the continuous moving force acting on the beam is given by equation 4. The loads are assumed to move at constant velocity, c, and epsilon is the gap between the two loads. Hence, the gravitational external applied fast-moving load is defined by equation 5, the boundary condition. It is rated for simply supported boundary condition, which is given in equation 7. It assumes that the initial conditions are given in equation solving the dynamic system. The governing fourth order partial differential equation of order 4 is solved by the method of finite Fourier transformation solved and is defined as below in equation 9 and 10. Thus, substituting equation 5 and 10 into system of equation 1, the result is non-homogeneous system of partial differential equation, which is given by equation. Then multiply each term in above equation by the function sin q per x per L and integrate in respect to x from between 0 to L. The boundary condition is taken into consideration. We obtain equation 11. Further rearrangement of equation 12, we obtain equation 16. Equation 16 is subjected to Laplace transform defined by equation 17, where S is the Laplace parameter. Applying the initial condition in 8, we obtain equation 17. Then subjecting equation 17 to some simplification and rearrangement give us equation. Equation 19 can be simplified as below. We have equation 20. The equation of equation 20 is defined by equation 23. Thus, the Laplace inversion of equation 20 is given by equation below equation. Next, equation above is substituted into equation 10, which gives us equation 31. Equation 31 above represents the transverse displacement of flexible structure under several loads when the loads are of different magnitude. For the load of the same magnitude, the expression above in 31 give the equation below, equation 33. When the loads are of equal magnitude and started their journey at the same point, so we have equation 23 becomes equation 34. Then we want to consider the second case. Here we consider harmonic loads, and the continuous moving force acting on the beam model is given by equation 35. Hence, the gravitational external applied fast moving is defined as equation 36, where all parameters are defined as before. Thus, in view of equation 1, take into consideration equation 36, once obtain equation 37. The governing equation in 37 above is the equation of the motion of flexible rotatory inertia and beam beneath several harmonic mobile loads. Fourier sine transformation method, like in the previous section, is hereby applied. As in previous section, the same procedure is strictly followed in this problem of vibrating system that involves harmonic load. Following the same argument as in previous section, and after some simplification and rearrangement, we obtain equation 40. Subjecting equation 40 as defined previously yields equation 42. Subjecting 42 now to Laplace transform in conjunction with boundary condition, we obtain 44. Further simplification, equation 44 yields equation 46. Next, equation 46 above is substituted into equation 39. So we have the equation below as given in equation 47. Equation 47 above represents the transverse displacement of flexible structure under several harmonic loads when the loads are of different magnitude. For the load of same magnitude, the expression in 47 becomes as given in equation 48. When the loads are of equal magnitude and started their journey at the same point, solution 48 becomes equation 49. The condition for resonance. In this segment, resonance phenomenon of our vibrating system is investigated. The transverse displacement of flexible beam, Rayleigh beam, may grow beyond bound when in equation 21 clearly shows that the flexible beam resting on elastic foundation will experience resonance effect whenever we have equation 50. While equation 46 also shows that they are the same beam under the action of harmonic variable magnitude moving load will experience resonance effect whenever we have the condition below in equation 51. Then the pressure profile in equation the pressure profile in figure 1 shows that when other parameters are kept constant, while we vary our foundation, flexible foundation modulus, as we increase the flexible foundation modulus, the deflection profile reduces. This to figure 2. Figure 2 displays transfer displacement of prismatic beam for various value of axial force. Next slide. The figure 3, the transfer displacement of the beam for various value of K1, that is our shear force. Then the next slide, the next figure in figure 4 also shows for the transfer displacement of the beam for various value of X0 gap between the two loads. Figure 5 also transfer displacement of the beam for various value of load 1, while other parameters are kept constant. Then figure 6 also shows that the transfer displacement of beam for various value of F2 when it's being variant parameters are kept constant. Figure 7. Transfer displacement of the beam for various value of our the third load, while other parameters are kept constant. Then we now compare, also do the same thing to harmonic load by comparing the deflection profile for the first problem, the regular load, and the harmonic load. So it's given in figure 15. Comparison of transverse displacement for problematic beam of steady and harmonic variable load. In this study, method of finite Fourier transform has been used to analyze the vibration characteristics of prismatic Rayleigh beam transversed by several moving loads. With the employed approach, the effect of various parameters have been investigated under the action moving several loads. Thanks for listening.